Hello everyone and welcome to this presentation on the problem minimize sort. In this session we will explore an efficient algorithm and its implementation in C++. In this session I will be guiding you through this exciting problem. The objective of the problem is simple yet intriguing. Given two integers num1 and num2, we aim to find an integer result that satisfies two conditions. The number of 1 bits in result must equal to the number of 1 bits in num2. The XOR between result and num1 must be minimized. The problem has straightforward constraints. We are given two integers as input num1 and num2, and we need to output an integer result that meets the specified conditions. To solve this problem, we use a couple of fundamental techniques. First, bit manipulation allows us to efficiently work with binary representations. Second, the counting of set bits, which refers to the number of 1 bits in a binary number. In C++, we can utilize the built-in function built-in pop count for this. We also apply a greedy algorithm to minimize the XOR. This involves prioritizing the most significant bits of num1 to reduce the XOR difference. If necessary, setting additional bits in the least significant positions. Let's break the approach into simple steps. In step 1, we count the number of 1 bits in num2 using built-in pop count. This gives us the target bit count for our result. In step 2, we iterate through the bits of num1, starting from the most significant bit and set bits in the result as long as the target bit is not met. In step 3, we still need more bits to match the count. We set bits in the least significant positions of the result. This ensures that the XOR is minimized while satisfying the required number of 1 bits. Here is the first part of the C++ code. We begin by defining a function minimize XOR. First, we calculate the number of 1 bits in num2. Next, we initialize a variable result to store our final result. Then we iterate through the bits of num1 from the most significant to the least significant, setting bits in the result until the target bit count is met. In the second part, if the bit count is still less than required, we iterate through the least significant bits and set them in the result. Finally, we return the result, which satisfies both conditions of the problem. Let's walk through an example. Suppose num1 is 3, which in binary is 1 1, and num2 is 5, which in binary is 101. The first step is to count the 1 bits in num2, which equals 2. Next, we copy the set bits from num1. Starting with 1 1, we use 1 bit, leaving 1 bit remaining. Finally, we add an extra bit in the least significant position, resulting in 110. So the output is 6, which is 110 in binary. Now let's analyze the efficiency of our solution. The time complexity is big O of 1 as we only iterate through 32 bits twice. The space complexity is also big O of 1 as we don't use additional data structures. This makes the solution optimal for all valid inputs. To summarize, bit manipulation is a powerful tool for problems involving binary operations. Built-in functions like built-in pop count simplify implementation. A greedy approach helps in effectively minimizing the XOR value. That concludes the technical discussion. Do you have any questions or feedback? And thank you for your attention. Before we wrap up, don't forget to subscribe to my channel. Here I share coding tutorials, problem solving strategies, and much more. If you found this presentation helpful, please like, share, and subscribe. Thank you for your support, and I will see you in the next